We are now going to wrap up this unit with section 8.5, applications of matrices. What you're going to find is we're going to kind of go full circle now and go back to applying these matrices to solve systems of equations, what we really started out with when we were in 7.3 of this unit. So the idea is we're going to apply these matrices to that and then know the dimensions you will need. In other words, know the setup that you will need. So an essential question that we've been addressing in this unit is how do I set this up and what processes are available for solving your system once you've set it up. Hardest part a lot of times is just knowing where to start, and that's that setup idea. And then finally we are going to use an Iowa Core standard, and that's going to be transform graphs or transform images. What you'll find is this is a major application in our world today with all the digital images that we have. And I mean, if you look at this screen right now, what's happening is there's projections of images on our screen, and if you ever are going to be doing something that involves that, transforming graphs by using matrices is something that we will use to project these images on these two-dimensional planes. Alright, this is a problem that we had that I gave to you a little bit ago, and the power of juice boxes really spurred you guys to act on this, and some of you were successful and got yourself a juice box. But now we are going to walk through this and kind of just put you in my mind of what I would be thinking to solve something like this. So the problem was that we needed to come up with a standard form quadratic that goes through the following 3 points. And the idea would be that you don't really know where the vertex is. None of these points are it. So it's not like you could use the vertex formula that y equals x minus h squared plus k, all times a, of course, don't forget that a. You can't use something like that in this situation. So now where to start? Well, I mean, start with your objective here. We're trying to find the standard form of a quadratic. So knowing that you don't want standard form, you know it's going to look something like this. And if you didn't know this, you could read in your books that this is standard form quadratics. Alright, so here is your quadratic in standard form, and now what you're trying to figure out is, hey, I need to go through these 3 points. What do I know and what don't I know? Well, in providing these 3 points, I've given you x, y values, so you could kind of play around with that and maybe see what would come out of putting in these x, y values. So I'm going to go ahead and do that for this first one, and what I would get out of this would be y would be the 8.5 equals, and then a times 2 squared plus b times 2 plus c. So all in all, this is going to come out to be 8.5 equals 4 times a, because I'm just going to square those and order doesn't matter when multiplying, 2b plus c. Okay, so there's my first equation, and you could then start to say, alright, what I'm really trying to find then is this A, this B, and this C. I need to fill in this A, this B, and this C. So this is where you would start to maybe think back to when I said, hey, if you have one unknown variable, all you need is a linear equation. You just need an equation with one variable. If you have 2 unknown variables, that's when you would have been back in like that 7.1, 7.2 section when you were solving a system of equations that had 2 unknown variables. A lot of those were lines, and we had the substitution and the elimination of columns, those 2 methods along with graphing, of course, to solve for those. We're dealing with 3 variables. We're going to need 3 equations, and that's what brought us to 7.3 when we went beyond just 2 unknowns. So in this case, what I am going to write is the equation 8.5 equals 4a plus 2b plus c. And then what we do know then is I need 2 more equations on top of this. That's where you could use those points right there. Now I'm going to go ahead and write those out. Okay, so this thing right here is something that we could have used 7.3 to solve by getting a 3, 2, 1. Remember when we were trying to aim to get a 1 variable equation so that we could back substitute to get the rest. Now this is something that we would have to do manually, and it took a lot of work, and sometimes we would write down the problem wrong and everything would be messed up. So we don't want to leave it to man to do a problem like this. That's when technology saved us. One of our questions, remember, was how do we set this up? We've got that, and what processes are available for solving this system? So this setup, what processes? Well, matrices, of course, and we have a couple ways that we could set this up. The first way was what we had covered was that augmented matrix, and that's when you took the coefficients and you slammed it next to the solutions into this thing that we would call an augmented matrix. So we would have this matrix right here of coefficients, 25, 5, 1, 1, negative 1, 1, and then we would have these as our solutions in our solution column matrix. But then we kind of slam them together and we have this dotted line, or this solid line is what I tend to use, as a separator of those two. And then what we could do, the option was, well, just like we had to for that 7.3 where we would get a 3, 2, 1 stair step, we're also going to get a 3, 2, 1 for this left-hand matrix, and we would want a diagonal of 1s. What we would call that is our REF form, or row echelon form. The idea then at that point is that you could just use back substitution to solve for the other variables, because essentially what you would have is a 1-variable equation, a 2-variable equation, and a 3-variable equation. I'm going to go even further and say get this into reduced row echelon form, so RREF form, and what you're going to get is this. So what this amounts to being is, when I took the reduced row echelon form and I put this 3x4 matrix into my calculator, I received this. And what you might wonder is, well, why is that important? How does that really help us? Well, don't forget, this was our A, our B, and our C column, right? A, B, C column. So what we had was 4A plus 2B plus 1C was equal to 8.5. Well, now what we have is 1A plus 0B plus 0C, so in other words, just 1A, is equal to 0.5. That's a point. Okay, and then this one would have been 0a plus b is equal to, and then negative 3, because that also wiped out. And finally, we had c was equal to 12.5. So there we have it, which was a lot easier than solving for our ABC up here. Now, the other thing is, don't lose sight of what you were trying to find. This was our objective. So what we do have to go back and do is say, well, now we have found my standard form quadratic where I have this A, B, and C to plug in now. Okay, so that's what we've been looking for. Another way to set this up, and I do want to show you this as well, is we could also use the idea that we can use our coefficients, our 4, 2, 1, 25, 5, 1, 1, negative 1, and 1 again, and we can multiply it by our unknowns, our A, B, and C, to be equal to that solution matrix. So the idea with this one is, once again, if you were to actually do this operation, I'll call this A times X. This is our unknown. We know our A is equal to this column solution matrix. If you were to multiply A times X, what you're going to get is 4 times A plus 2 times B plus 1 times C. So that would have been this very equation right there, and we're saying, well, it equals 8.5. And then same thing if you were to multiply row 2 by this and then row 3 by this. So now what I want to say is, well, what we were trying to solve for is this guy right here. So could we undo this matrix that sits here? And we found that normally you would think, hey, I would divide by A from both sides, but since we don't have that option, what I'm going to do is A inverse times A to wipe that out. And so same thing here, and on the same side you would have to do it. Since I did it on the left here, I'm going to have to do it on the left here. So there we have what we need to do. So we're going to have to find A inverse, and that is something that you could just simply do on your calculator. Enter this matrix A into your calculator and then go ahead and calculate A inverse. Alright, so the idea is with this A inverse that I calculated on my calculator, I could multiply A inverse here, so I'm not going to write it, but I would have to take this matrix times this matrix right here, and they would cancel each other out to become that identity matrix, which is the equivalent of 1, right? When we were like multiplying by 1 times anything, it would just be that anything. Same thing with this identity. An identity times this ABC would just be this ABC. So therefore I got X by itself, but now I just have to take this A inverse times this B matrix right here. So really, I just have to multiply these guys. Right? When I would do that, believe me or not, I would try it if I were you. What you are going to get is X is equal to, and then these multiplied together is going to get a 0.5, negative 3, 12.5. And what we did know was X was really just this A, B, C matrix. So therefore A is equal to 0.5, B is equal to -3, and C is equal to 12.5. I want to show you then. So if I were to move this about, so here you can see those are my points that I've just plotted. And what I have now is this equation where I've discovered that Y is equal to 0.5x squared minus 3x plus 12.5. And what I want you to see is, yes, we have achieved an A, a B, and a C that would give us a quadratic that goes directly through those points. Tomorrow in class, what we will be working with is a problem like this, but I wanted you to just get rolling with the idea of, what if I had a degree 3 polynomial with this list of values? Could you find the line of regression, or the regression that is going to go through these points? Okay, so there's the list. I want you to come up with the degree 3 polynomial that will best fit these points. The final thing is, we're not going to get into it too much because also on your worksheet you'll work with this, but we are going to be doing transformations, and these can be transformations of images, or these can be transformations of images including vectors. Vectors, of course, are those visuals that we would put out for ourselves that represent a magnitude and direction. So what we do is we place these initial and terminal points into matrices using columns. So for example, something like this we used to represent in component form, where we would say that this has a direction that we would go +3 in the x direction, or the horizontal direction, and +2 in the vertical. So 3, 2 was the component form that we used to use. Another way of doing this is to look at it something like this, 3 to 2 as a matrix. And we could add other vectors to this, such as this. This would be the equivalent of 1, 2, because it was over 1 up 2. So 1, 2. You could have also had something like this, back 1, up 1, so back 1, up 1. So there's your system of vertices and of this image that could be happening there. The idea is, what if I wanted to enlarge this image by, let's say, 2, so make everything 2 times the size? Well, you would have to go in and multiply that by 2, multiply this by 2, and multiply this by 2, which this was -1, 1. So you could also do it as a vertex, or as a matrix, where you do scalar multiplication. And what you would just go in and do is, oh, this is 6, this is 2, -2, 4, and again, your calculator could do this much faster, but now you have these new points where, hey, I need to go over 6, up 4, so something right around there. That would have been this vector stretched out. 2, 4, over 2, up 4. So what you're creating is another image to this image, but just 2 times bigger. Okay? And you can do it in a very fast way, because there can be some very complex images out there that you could be working with, and you need to enlarge everything about it. Alright, I'm not going to necessarily do this one, but we're going to be playing around with this more. If you wanted to set this up, it would look something like this. This point, also, not just of vectors can be represented, but points, any kind of images. So if we looked at this point, we're at 2, 1, so I'm just going to write 2, 1. This point right here is 2, 2, and then we have 4, 2, and then we have 4, 1. So this is kind of the system that I'm looking at, and we can do many different kinds of operations on this. I would be interested for you to try this operation. If I did a 1, 0, 0, -1, see what this would do. Go ahead and do that operation, and then we'll describe that in class, and then as well as explore other transformations.